Hi, my name is Jim, and today we're going to be discussing operational amplifiers. And the technique we're going to use is called current pushing, and this is perfectly valid, and it corresponds to the gain formulas. And the assumption is that the open loop voltage gain is much higher than the closed loop voltage gain, and that's typically the case. So we have our operational amplifier here. The negative is the inverting input, and the positive is the non-inverting input, and the input resistance between these two is fairly large. So what that does is it gives us the ability of not have to worry about the op-amp's input pins loading down any signals we may have at the input. Now, the input bias currents are present, but usually very, very much smaller than any currents we're going to be talking about. And in JFET op-amps, the bias currents are basically insignificant altogether. So none of these built-in errors like input offset currents and so forth are going to be causing us any trouble in our analysis using current pushing. Now, realistically, if we're dealing with 5% resistors, or for that matter 1% resistors, they're going to swamp out any of those effects anyway. So what we're going to start here is by grounding the non-inverting input, and with the feedback path, what that means is that through feedback is that the node here for the inverting input is just about the same voltage. Now, it's slightly different, but it's very, very close. And what we can say about that, if we have 2 points that are the same voltage, and if they, say, follow each other up and down, it looks as if they are virtually shorted. Doesn't mean there's a wire there, doesn't mean any current flowing in and around here is going to be down here, but virtually shorted. So this situation allows us to do some very nice analysis with op-amps, and it's only true if the operational amplifier is operating in a linear capacity. That means it can't be hitting a supply rails causing a clip. It can't have positive feedback as comparators would have, which is nonlinear operation. It has to be linear, where the output voltage is a function of the input voltage in a linear manner. So having said that, I've parted this up a little bit. This is the input resistor Ri, it's 1K, and our feedback resistor RF, and that's typically the designations given to them, is 10K. And since I have 0 volts here, by the nature of the feedback, I have 0 volts here. Now what really happens is VID is across these 2 pins, V input differential, and that's a very, very small voltage which is amplified a whole lot by a very large gain. And when that feeds back, we can say that that, for all practical purposes, is 0 volts. So from there we'll start our analysis. What we see is this is -2, and what we know is that 0 volts is more positive than -2 volts, so we have conventional current flowing in this direction through the 1K resistor. Now, to find out how much that current is, it's simply using Ohm's law here. We have 0 minus a -2 volts divided by 1K gives us 2 milliamperes. Now, since the input resistance of the operational amplifier is very high, the way we analyze this is we say that this current is going to also be pushed through the feedback resistor. Now, all of this is the function of the gain of the amplifier, but in this analysis, it doesn't look like that. So this is kind of a model that allows us to come up with an analysis method which is very effective at determining the way operational amplifiers would behave in a circuit. So if we have the same current flowing through our feedback resistor here, RF, and we elect to find the voltage drop, DROP, that's very important. A voltage drop may or may not reference ground. It may or may not reference 0 volts. It's a drop across the part. It doesn't say what that part is anchored to. So we know here that if we calculate the voltage drop, we end up with 20 volts. Now, actually, that's kind of a bad voltage from the standpoint of a practical operational amplifier, which typically would rail at plus or minus 15 volts. But for the sake of the example here, I'm going to use it anyhow. So I have a voltage drop across this part, and what I need to do is write down the polarity of that. So since this current is flowing in this direction, so is this current. And that's producing a plus-minus drop across the resistor. Now, to find out what the output voltage is we're going to have to basically figure out one end of the voltage on that resistor. And what we know is that the left end is connected to 0 volts. So what we can say about that then is that the right side of the resistor here, as drawn, is more positive than the left end by 20 volts. Since the left end is 0 volts, the output voltage is going to be plus 20 volts. So anchoring allowed us to determine that, and let's take a look at the formula here for an inverting amplifier. And this is the transfer function of it, V out divided by V in, and that is equal to negative the feedback resistor divided by the input resistor. So what the negative means is that it's going to be out of phase. Case in point, negative voltage in, positive voltage out. If we were to say look at a sine wave, we'd see this polarity going in and this polarity much larger coming out. So in the case of a sine wave, without any other anomalies, we're going to be 180 degrees out of phase. And that's what the negative sign means. And if you think about it, going back to AC circuits, J squared is equal to -1, and that takes a phasor on the real axis and moves it over to the imaginary axis. And it's exactly kind of the same as what we're doing here. So in this simple configuration, we can see that the output is 20 volts, and we've done that by pushing currents in an inverting amplifier. Now let's take a look at an inverting summing amplifier, and again we're afforded the luxury of having the non-inverting terminal grounded, hence we can say that this is 0 volts. And to figure out what our output's going to be is, well, we kind of have to know what the current flow through the feedback resistor is going to be. Now, as before, the feedback resistor is going to be anchored at 0 volts, but the question becomes is what is the current flowing through it? So there's a lot of ways of solving this, and what I elected to do was just to figure out what the current's going to be given our input voltages going around this loop. And from that point then I can determine what current is going to be flowing through the feedback resistor. So I've done that here, is pull this out of the schematic to make it a little simpler, and this point is 0 volts. Again, it's a virtual voltage, but it is 0. And I know here that if my current here is going to be 2 milliamperes flowing in this direction, so we see that I2 is going to be equal to 2 volts, M, minus 0 volts, M, divided by 1K is equal to 2 milliamperes. So that's where my 2 mils comes from. Now, on the upper leg here, we have -1 volt, and 0 is more positive than -1 volt. So the math on this says is that 0 minus a -1 volt will give us 500 milliamperes, and I use arrows to indicate the direction of current as opposed to assigning them positive or negative. I do that because the arrows are very clear to me of what's going on, and I don't need to be dealing with a negative current or a positive current when I'm trying to figure things out. I don't want a mathematical solution, I want a correct solution. And anything I do that will allow me to see better into the analysis is what I want to do. So 500 mils flowing this way, 2 mils flowing this way means that, according to KCL, we have 1.5 milliamperes flowing through our feedback resistor. Easy enough. So now what we're going to do is find out what the voltage drop is across that feedback resistor. So we know we have 1.5 mils flowing, it's 5K, and if we do the math on that, we find out that the voltage drop across this is going to be 7.5 volts. This is the drop across this. Now, from the direction of the current flow, what we can say is that the right side of the resistor is more negative than the left side of the resistor by a factor of 7.5 volts. Further, since the left side of the resistor is anchored to 0 volts, this then becomes 7.5 volts more negative, and the output of this would therefore be negative 7.5 volts. Now, if we'd like to verify that using superposition, we can do that, and superposition is a fairly nice way of figuring out linear circuits. And what we do is we only let one source act at a time. We end up with a partial result, and then we go back and we let the other source act alone. We end up with a partial result, and then we add the two together. So if we take the first case here, our input is negative 1 volt, and we don't have the 2 volts anywhere in this. We're just going to figure out what this is going to do. What we end up with here is a voltage negative 1 volt, and the gain of this is going to be 5K divided by 2K, and that's going to be equal to plus 2.5 volts. So I'm using the equation here to do this. I could push the currents if I wanted to. It would produce exactly the same results. Secondly, I'm going to analyze the circuit with plus 2 volts. And again, I'm going to use the equation here. V out is going to be 2 volts times the gain of this circuit, which is 5K over 1K. So the gain is going to be different for both of these inputs as scaled by our input resistors. And that gives us an output of negative 10 volts. So if we now have both of our partial results, we add them together. Negative 10 volts plus 2.5 gives us a negative 7.5 volts, which is exactly what we had in the beginning. So superposition is going to be a tool which we can use later on when the inputs, especially down here, have multiple inputs and we don't have the luxury of this being 0 volts anymore. So let's look at a non-inverting configuration, and here what we have is the input signal, which in this case is 2 volts DC, applied to the non-inverting input, and once again we have a virtual short between the two pins, which means that the inverting pin is going to be at 2 volts. Now from that we can determine the current flow, which is going to be from positive 2 volts to ground. And the current flow through what I call resistor 1 is going to be 2 volts minus 0 volts, just being thorough, divided by 1K equals 2 milliamperes. Now, since we have 2 milliamperes flowing down here and 0 coming out of the op amp because it's a large input resistance, we can immediately say that we have 2 milliamperes flowing through the feedback resistor, R sub F. So, next part of this is to figure out what the voltage drop. DROP is for R sub F, and that's simply going to be I times the value of the feedback resistor. 2 mils times 2K equals 4 volts, and I've put the word drop behind it. Now, kind of what you should be realizing is that I'm trying to make a point with the word drop. So to figure out what the actual output voltage is we take our 2 volts, which is on the left side of the feedback resistor, and we have a 4 volt drop across this, giving us, with the current flow, a plus to minus polarity. And what we know then is that this is going to be more positive. The right end of the resistor is going to be more positive than the left end by 4 volts. Therefore, our output is going to be 2 volts plus 4 volts is equal to 6 volts. So if we go to analyze this with the formula, again, this is the transfer function of the circuit right here. It's a non-inverting configuration, and solving for V out, we have 2 volts times 1 plus the ratio of RF over RI gives us 2 times 3, which is 6 volts, which is exactly what we had before. So that would be a non-inverting amplifier. And the gain on this, by the way, would be plus 3. Now, if we have a non-inverting summing amplifier, things get a little bit more involved. And fortunately, what we have is our inverting input is grounded. Again, what we have is a virtual short across this, and what our mission is going to be is to figure out what this voltage is, I call it V+, at this node. Further, the op-amp does not produce any load on this, so we can kind of treat this as an open circuit. So I've elected to do this, and again, there's many ways of doing it, by just figuring out what the current flow is going to be, figuring out what the voltage drop is across the resistors, and then doing some adjusting depending upon what resistor I'm talking about regarding an anchor point being here or here. Notice that I've just disconnected the op-amp altogether. Not going to be 0 volts. So one way to do this is to find a current, and the current would be flowing in this direction because 2 volts is more positive than negative 3 volts. So our equation would be I equals 2 volts minus a negative 3 volts divided by the total resistance, which is 2K plus 1K. Gives us 5 volts over 3K, which is 1.66 milliamperes. Repeat. So I know that, and next what I need to do is find out what the voltage drop is, and the resistor I've selected here, it can be either one, it does not matter, is our 2K guy. So to find the voltage drop, it's simply Ohm's law. That's going to be 1.66 repeat milliamperes times 2K. Means that we have a 3.3 volt drop across the resistor. And that would look like this, and the polarities would look like that. Now, once I know that, I'm in a good position to figure out what the actual voltage is going to be at this node right here. And if I take a look at this, is what I'm going to see is that if this side of the resistor is anchored at 2 volts, plus 2 volts, and if I have current flowing in this direction and have a drop of 3.3 volts, that means that this side of the resistor is going to be 3.33 volts more negative than this side of the resistor. So, if we take a look at that, we have 2 volts minus 3.33 volts, and the voltage at this point is therefore negative 1.33 volts. So finding the voltage drop isn't good enough. We had to anchor one side on a voltage we knew to figure out what this node voltage would be. Now once we have that, well, things pretty much fall apart. I've redrawn the op-amp here without the resistors and just made this negative 1.33 volts by virtual short. Move that voltage up here, and then what I can see is current is going to be flowing in this direction because negative 1.33 volts, where am I at here, is less positive than 0 volts, so my current is going to be in this direction through the 1K resistor. And what I need to know is, what is this current? And the reason I need to know that is because I'm going to push this current through the 4K resistor. And then when I do that, I'll be able to find out what V out is right here. So the current flowing through this resistor is going to be equal to 1.33 volts divided by 1K, which ends up being 1.33 milliamperes. Good enough. Now let's find out what the voltage drop in the 4K resistor is. That's straightforward. We know the current flowing through it. We know the value of the resistor. So that's going to be 1.33 milliamperes times 4K, and that comes out to be a 5.33 volt drop. So I'm not saying that's positive or negative. I'm just saying it's a drop. Now, when I apply the current directions to it, what I can see is that the right side is going to be more negative than the left side by 5.33 volts. So the very last thing I have to do is to anchor this side of the resistor and figure out what the total is going to be that appears at V out right here. So pulling out this resistor to make it a little bit easier to see, I've got this side being negative 1.33 volts, a 5.33 volt drop plus to minus, which means that this side is going to be 5.33 volts more negative than this side, and that'll give me a V out of negative 6.66 volts repeat at the output of the operational amplifier. So that was a little bit more involved, and if we elect to verify that with our equation for a non-inverting amplifier, is our V out is going to be equal to our V in, which is going to be this guy here, 1.33 volts as before, times the gain formula is 1 plus RF divided by RI. That would be this RF and RI. And that gives us V out equals to negative 6.66 repeat volts, which is exactly the same as we determined by pushing the currents. So in this case, we had some additional difficulty here dealing with these two resistors, and we didn't have the luxury of this being forced to be ground. So this problem is a bit more difficult than the previous one. And that's also not inverting, so configuration. There you go. Sticky little guy. Alright, our next guy, this is even more involved. So what I'll do is deal with these three resistors, and we have some additional complications here, as you can see. One is we have one more input here on our non-inverting input, and secondly is we also have an input on the inverting input. So what we're going to have to do to figure out this first, so we always want to figure out what this voltage is first, then by virtual short come up here, and then we can solve the rest of it in somewhat of a straightforward manner. We're going to have to be using some analysis techniques, and the choices we have are mesh, branch, nodal, superposition, and possibly some other type you can might think about. And the whole mission here is to find out what V plus is. So there's some steps in here, and then what I'll do is take this up in part 2. Thank you for watching.